Let's crank this chapter out. Not sure how long it's going to take, but we have one little thing left, and that is called molarity, which is a way that we report concentration of a solution here, right? So that's what it's all about, right? I can calculate based on a balanced equation how many grams or how many moles of a solute I need. But how do I do that if I'm using concentrations? And so percent really doesn't work very well, because if I use like a 20% solution of, let's say, sodium chloride solution, that means that there are 20 grams of sodium chloride dissolved in 100 milliliters of solution. Okay, so to be clear, that is, you take 20 grams of your solute and you add enough water to make 100 milliliters of total solution, which is similar to how molarity works, except molarity uses the number of moles in 1 liter of solution. All right, so it's in a way it's the same way. It's just a different kind of concentration, but you would take 20 grams, and this is the solid, and then you add enough water, making sure this dissolves, to make 100 milliliters of solution, which means you can use this conversion factor here. 20 grams of sodium chloride equals 100 milliliters of solution, for example. You could, or you could just apply the percentages here, realizing that it's grams of solute per 100 milliliters of solution here, right? So how many parts in 100? That's what a percent is, right? Part divided by total times 100 gives you percent. And the reason we have two different units here is because we're using a solid as a solute and a volume as a solvent. And so it turns out that 1 gram is equal of water is equal to 1 milliliter of water, and that's because the density is 1.0000 grams per milliliter. So remember, that's the density of water. But that's not very useful, right? So if I had a reaction that's, let's say it's hydrochloric acid and sodium hydroxide, that's a neutralization reaction. So I want to perform this reaction, which forms, of course, sodium chloride and water. And if I had a 20% solution of hydrochloric acid and a 20% solution of sodium hydroxide, adding 100 milliliters of each does not necessarily neutralize that solution, okay? Because we need to look at the number of moles, because if we can do one mole of hydrochloric acid, it's going to need exactly 1 mole of sodium hydroxide. So what we use is molarity, and I'll talk about that here in a second. I just want to address some of the other buzzwords that are here, right? We already know that all solutions are homogeneous mixtures, and it doesn't have to be a solute of a solid or a liquid that's dissolved in water. It could also be air, right? Air is a solution. We can't see the difference in components, but we know there's nitrogen, oxygen, carbon dioxide, and others in there. Coca-Cola, well, I don't know about that necessarily, only if it's flat, right? Otherwise I can see the carbon dioxide forming. Brass is a mixture of 2 metals, but those are technically also solutions. Of course, we're only interested in aqueous solutions at this point. Solutions have 2 components. The solute, talked about sodium chloride being a solute here, water being the solvent, and defining what 20% means. And the concentration refers to how much solute is in total in your solvent. These two are again just vocabulary. Dilute means not fully saturated, or, well, here I'm throwing out another word, right? So dilute means weak, right? You have maybe like a 5% solution versus a 30% solution, and then if there's also a solubility limit, right? So let's say sodium chloride, and I can actually look up what the solubility limit is here. We have a chart. So this does a couple of things here. The temperature also affects solubility here. Looking at room temperature, about 25 degrees Celsius, what we have here, and I don't have sodium chloride here, so let's use a different example. Let's use sodium bromide. Okay, so what this means here, that I can dissolve, this is how much solute I can dissolve in grams. This here is grams of solute in 100 milliliters of solution, or 100 grams, which is interexchangeable here, right, in 100 milliliters of solution. So at room temperature, 25 degrees, if I take this up, I find that I can actually dissolve 120 milliliters of, I'm sorry, grams of sodium bromide. So okay, so that's quite a bit. That's a pretty high concentration, but that's its that's its limit, right? So if I have a concentrated sample of that solution, that means I'm pretty much maxed out at the limit here at 110 grams or so at room temperature. Let's say 110 grams. That's concentrated. If I only dissolve 10 grams or so, then that would be dilute. What is also interesting to notice that not all solutes increase with temperature. The solubility of some of them doesn't increase at all. Like sodium bromide happens to be fairly flat. Same with potassium nitrate. And there's a slight increase. Potassium chloride. Potassium nitrate actually is almost linear. In the regular semester, we actually do a solubility lab for potassium nitrate because it is so nice and linear. But we don't have that in your lab kit this time around. So anyway, so you do see somewhat of an increase in solubility for some solutes like potassium nitrate, but some of them are flat. And then there are things that are gases here, for example SO2, and carbon dioxide is another example. Your carbonated beverages have carbon dioxide as a solute, and so that doesn't really increase, that you're going to be pushing out the gas. But there are chemical reactions that are involved in suspending these gaseous solutes. So that's an entirely different story, saved for UChem 2. And if you remember what I told you about sugar, look how highly soluble it is. You can get 200 grams of sugar into 100 grams of water. And if you heat that up a bit, just a little bit above room temperature, you can get like 280 grams, almost 300 in. And that's what makes the syrupy kind of maple syrup. And honey is also an example of that. So some substances are sparingly soluble or not at all. And this is just a small example of that. Okay. So chemists like to report their concentrations in molarity. Molarity is abbreviated with a capital M. So if I have a 12M solution of HCl, hydrochloric acid, that is referred to a 12 molar hydrochloric acid. That means I have 12 moles of hydrochloric acid dissolved in 1 liter of solution. Same idea. The book has a really good picture, and I'll draw it since I forgot to incorporate it here. It has a so-called volumetric flask, and they don't really look like that. So okay, let's just say this is exactly 1 liter, 1.000 liters. Best I can do. So it would take 12 moles of hydrochloric acid, and hydrochloric acid is not a solid, but somehow they put it in there and then fill it up to 1 liter, so that in 1 liter of solution you have exactly 12 moles, right? So moles of solute dissolved in liters of solution. Really not very difficult, and that can be used as a conversion factor, of course, right? You can then calculate how many moles are in 200 milliliters of solution, or if you need 8 moles, how many, and you have a 12 molar solution, how many liters or milliliters do you need to measure out to neutralize, for example, since we're talking hydrochloric acid. But let's just work a few of these step by step, approaching more complicated problems one at a time. This is just asking for molarity. What is the molarity? So we're asking for M. That means we need to know the number of moles of solute divided by the milliliters of solution. I'm sorry, the liters of solution here, right? So what is the molarity of a solution where 0.567 moles of sodium chloride are dissolved to make 250 milliliters of total solution? So we're given the solute, which is 0.567 moles of NaCl divided by, now I'm given the total solution in milliliters, and you have to remember that there are 1,000 milliliters in 1 liter. So I move the decimal over, that's just a reminder, so I have to divide it by 0.250 liters, and that gives me a molarity of 2.27 m NaCl. M tells me the type of concentration. It's not percent, it is molarity. Capital M tells me moles of solute divided by liters of solution. So that's it. And we don't have 3 significant figures here. We have 2. So this is technically just 2.3 molar NaCl. Something to remember are your significant figures. This is nice, it has 3, but there is no certainty about this, so there are just 2 significant figures. What is the molarity of a solution where 0.56, didn't I just do that? Oh, okay, there must be, I have the, yeah, once again I have nicely everything calculated out. And so obviously the way I've written it, it would indicate that there are 3 significant figures, but if I just give you 250, there's no decimal here. That means this is actually 2.3 m, and I'm going to have to fix that for next year. Okay, moving right along. What is the molarity of a solution where 27.6 grams, now I'm giving you grams, right? So are dissolved to make 150 milliliters of solution. Okay, so we have the same problem. Once again, we have 150 milliliters, which is 2 significant figures. Let's see. Anyway, but we're given grams, so obviously you're going to have to convert grams to moles, and that we can do in our sleep. 27.6 grams of KMNO3 times 1 mole of KNO3 divided by 101.106 grams of KNO3. That's the gram to mole conversion. This gives me 0.273 moles of KNO3. And then if I want molarity, I take those moles, 0.273 moles of KNO3 or potassium nitrate. Again, I'm going to move the decimal over to convert to liters, divided by 0.15 liters, 2 significant figures, which gives me a molarity of 1.8 m KNO3. Let's go see what Genius Franz has here. Yes, he screwed up the significant figures. Okay, good job. Yeah, okay, those are just 2 steps. And yes, here are the significant figures here that I screwed up. Yes, I'll take a point off from my final grade, I promise. How many moles of lithium bromide are contained in 257 milliliters of a 0.100 m solution of lithium bromide? Okay, so now I'm going to use the molarity as a conversion factor. Having a 0.003 significant figure m solution of lithium bromide means that there are 0.100 moles of lithium bromide dissolved in 1 liter of solution, and that's exactly 1 liter. Okay, so I only look at the sig figs here and here, so I have 3. And now I use it as a conversion factor. I say I have 0.257 liters of solution times 0.100 moles of LiBr divided by 1 liter of solution. The liter of solution cancels and my answer is in moles of lithium bromide, which is what this question is asking. And the answer is 0.0257 moles of LiBr. Okay, so here I don't have a, okay, that's beautiful. Okay. All right, how many grams of iron 2 nitrate are contained in 1.5 liters of a 0.0250 m solution of iron nitrate? So here I have again the conversion factor, which is 0.0250 little m moles of iron nitrate, and that's something you should also be able to do, equals 1 liter of solution. That's the conversion factor. I want to know how many grams of iron nitrate are contained in 1.5 liters. Okay, so that's going to be 2 steps. I can calculate, and it's, you can do this probably in your head. You can say, okay, it's 1.5 liters, so it's 1.5 times that, 0.250. Okay, fine, but let's set it up anyway here. 1.50 liters of solution times 0.0250 moles of iron nitrate divided by 1 liter of solution. I already crossed through that on accident. That gives me the number of moles. And then all I have left, okay, so that's 0.0375 moles of iron. Hey, let me fix this here. FeNO32. And but of course I'm asked about grams, and I can do moles to grams pretty easily here, right? So I can do 0.0375 moles of iron nitrate times molecular weight, which is 179.86 of iron nitrate divided by 1 mole of iron nitrate. Left the iron nitrate out, but there you go. That gives me 6.74 grams of iron nitrate. Okay, so you see you couldn't have answered this question without knowing your naming, right? Because you cannot calculate the molecular weight without knowing what iron 2 nitrate is. So this is important that you remember the stuff you learned in the first week. All right. How many grams of iron? Oh, that's the same question, of course. Here is the solution. That gives me the number of moles of iron nitrate, and here are the grams of iron nitrate. Okay, so let's say I wanted you to solve this problem here. How many milliliters of a 2.5 molar sodium chloride solution would be required to prepare a 0.1 molar solution if diluted to 1 liter? So I've got a stock solution here. It is 2.5 molar in sodium chloride, and I want to dilute it. Okay, I want to use it to make 1 liter of 0.1 molar solution here. Okay, so I can use this formula here. The initial volume here, the initial volume times initial concentration or molarity equals the final molarity times the final volume. And so I know what the final volume is. The final volume is supposed to be 1 liter, and the final molarity I want it to be 0.1, and I know my initial molarity, which is my stock solution, of 2.5. So I use algebra to solve for volume. I want to know how much of the initial solution I need. right? So I'm going to need like 40 milliliters or 50 milliliters or whatever, and then add enough water to that to make a liter. That's what's happening here. So VI is going to equal MF times VF times MI. So we're talking about a 0.10 molar solution times 1.00 liters divided by the 2.5 M. See, the M cancels and we end up with liters here. Of course, I'm asking for milliliters. And what I get is, when I put that in, I get 0.040 liters of stock solution. And if I convert that to milliliters, of course, that's going to be 40 milliliters. Here, that's the solution. All right, let me take a little break and then work a few more of these.